Now in topic 5 of chapter 2, we're going to look for the zeros of polynomial functions. And to give you an idea what the zeros are, here we have a typical graph, and some quadratic function is going to, let's get a pen going here, going to look like so, let's say. And wherever it crosses the x-axis, the y value is 0. So we are finding the zeros. That is your x-intercepts. Okay, that's what we're looking for. And there's a number of protocols that we follow to get to it. Looking at the objectives, we want to use rational zero theorem to find possible rational zeros. This is like one of the little tools we have. And then find the zeros of a polynomial function. Solve polynomial equations. Use the linear factorization theorem to find polynomials with given zeros. And use Descartes' rule of signs. Now, this is the rational zero theorem developed. But basically, we're going to take the letters P over Q to find all the potential zeros. That's where this comes from, and we're going to show you the protocol for that as we go on. So in this particular equation that we're looking at here, this function, what is our P and what is our Q? Well, P is the constant here, and Q is the numerical coefficient of the term with the highest degree, which is x to the fourth. So this is our Q term. So we have the constant -3 and the coefficient 4. And basically what we want to do now is find the factors of a -3, and then later the factors of a +4, keeping in mind that they're plus or minus. So as we see this here, and let's go to the whiteboard here. We want to keep that and get rid of some of this. So our factors of P then will be plus or minus 3 and plus or minus 1. And the factors of 4 will be plus or minus 4, plus or minus 2, plus or minus 1. Now, what we do then is list all the possible combinations. So we can get plus or minus 3 over 4. That would be 1. Plus or minus 3 over 2. Plus or minus 3 over 1. And then we're going to get plus or minus 3 over 2. Plus or minus 3 over 1. And then we get plus or minus 1 over 1. Let's go back to the regular screen. So using the rational zero theorem, we ended up with the possible rational zeros. All right, let's go on to another example. And here we see a new equation, a new function. Our Q value is 1. Our P value is -2. So what are the possible rational zeros? Well, it's going to be factors of -2, which is, or are plus or minus 2, plus or minus 1. And for our 1 value for Q is just plus or minus 1, which is what they're showing here. Now, as we take each of these, 1 over 1 is 1, and 2 over 1 is 2. So we have a possible plus or minus 1, a plus or minus 2. Now, for this, we're going to go back and use synthetic division that we had earlier to see if we can factor this. Now, in synthetic division, remember we're going to pull from our original equation just the coefficients. So there's a 1, there's a 1, there's a -5, and there's a -2. And we're going to test these values to see if there is a zero remainder. If there is a zero remainder, then this value here is one of the zeros. So we try -2, and I'm not going to go through all of this, but we find out that we get a remainder of a +4, so that's not a zero. So this is not a potential zero. We put in there the -1 and go through the process. Again, this is not a zero here, so a -1 is not a potential. As we continue trying the potential zeros using synthetic division, if we use a 1 going through the process, again, we don't end up with a zero here. So 1 is not a potential zero. But now we use the 2. And when we go through the synthetic division, and let's just do one here. So again, you know where we got our values, 1, 1, -5, 2. And then we just bring the 1 down here. And then we go 2 times 1 is 2. 1 and 2 add up to 3. 2 times 3 is 6. Add this up, we get a +1. 2 times 1 is 2. And then our n column here is a 0. So now we know that 2 is a rational zero. What does that mean? Well, that means in our graph, this is going through at 2. We have found one of the zeros. Well, now we have to do some converting. Here is what we started with. This is what we ended up with. But what does this mean? Well, remember it's going to be 1 degree less than this. So this is going to be 1x squared plus 3x plus 1. And we can write that here. X squared plus 3x plus 1. And since we use x as a 2, we know that in this original factoring, this was the opposite sign. So we get with this factorization, because remember, when we take each of these and equal it to 0, this is where we get our x equals 2. But now, what about this? We want to find the other zeros here. Well, we can take this, and is it factorable? And the answer is no. So what do we do then to find what x is in this portion? Well, here we have to use the quadratic formula. And we've done this before. Our a is 1, our b is 3, and our c is 1. Substituting that into the quadratic formula, we get this. So what does this tell us? Well, our solution set is a 2 that we knew, and then it goes through 0 at this, and goes through 0 at this. Now, remember, these are all ordered pairs. This is going to be 2, 0, and this is going to be this, 0 in parentheses. But as we list it here, all they wanted were the x values. We have found the zeros of this using the rational zero theorem, synthetic division, and the quadratic formula. Wow. Now here we're going to look at some more background properties of roots of polynomial equations. Well, you recall from a long time ago, when an equation is of an nth degree, that is, whatever this highest degree is, you should expect this number of roots, that is, solutions, zeros. Now, if the result is an imaginary complex number, then there is, for this one, there's also the conjugate of it. And just to review conjugates, a plus bi, a minus bi. So they're saying here, imaginary roots, if they exist, occur in conjugate pairs. So going into another example, example 3, our q value is 1, our p value is 13. So to use the rational zero theorem, p over q, our p values are 13, and the factors of 13 are 13 and 1. I would write it the other way, but let's follow it this way. And over 1. So what are our potential rational zeros? Well, it's going to be a plus 1, a minus 1, a plus 13, and a minus 13. So how do we see which one would work? And if you said, let's use synthetic division, that's exactly where we're going. So setting it up for synthetic division, remember there's a 1 there. So our plus 1, minus 6, plus 22, minus 30, plus 13. And we're going to start with a negative 1. And again, you bring the 1 down, and then -1 times 1 gives you a -1, and so on. But when you get to your remainder, it's not a 0. So a -1 is not a 0 in this equation. So let's try a positive one. If I were doing it, I would have tried the positive one first. They're just showing you the protocol. So again, bring the 1 down and following through. And again, this is tedious. You can't make any arithmetic errors here. You end up with a 0 remainder. Therefore, 1 is a factor, a possible 0. Now remember, this came from a -1 as a factor, because if you equal this to 0 here, x is going to be 1. That's the one we're using. So when we do synthetic division, it's the opposite side of what's in this place. Now, we then end up with this. So you might say, well, what do we do with that? Well, again, we want to use the rational zero theorem to find out what would be our potential zeros of this. Now, I've always liked the way they set these slides up because they're repeating what we've done so far. So now we want to do, this is our Q, which is still a 1, and our P is still a -13. So we get the same potential possible rational roots. So 1, -1, 13, and -13. So again, you might say, what do? We go to synthetic division. So in this case, they are starting with the positive 1 and following through. Our remainder is 0. So 1 is another potential 0. So we have now this, and then converting this to its algebraic form. Remember, it's going to be 1 less than the 3 that we had there. So this is going to be to the x to the second power, x plus 13. So we have 2 of the factors. Remember, this is x equals 1, x equals 1, and this still equals 0. Now, this is not going to factor. So again, how do we solve this? The quadratic formula, exactly. So let's go on to the quadratic formula. Now we have all of this. We're going to solve this. And again, our a value is 1. Our b value is a -4. And our c value is 13. Putting that into the quadratic formula, notice what we have under the radical sign. We have the square root of a -36. Well, this is going to be an imaginary number, and that simplifies to plus or minus 6i. But notice we had to complete this by factoring out a 2 here. Let's just do it here. 2, and then 2 plus or minus 3i all over 2. Here the 2's cancel out, and we end up with this. So notice what our zeros are from that original equation. It took us a long time to get there. Positive 1, a positive 1, and then 2 plus or minus 3i. This portion, remember, is a complex number. Part of it is real, part of it is imaginary. Another background item, the fundamental theorem of algebra. If the function is a polynomial of degree n, where n is greater or equal to 1, then the equation, that function when it's equal to 0, has at least one complex root. And this refers to complex numbers that we just mentioned. We're now going to look at the linear factorization theorem. Now, it looks a little complex here, but essentially it comes down to having a function with some coefficient here, and where you are multiplying the various factors of that function. And I'll give you an example of it here. And we're thinking that each linear factor has a leading coefficient of 1. So in example 4 now, we'll see this in action. And I've picked up some of the information by reading this. It says the real coefficients, and in a sense our zeros, are a -3 and an I, and y, when x is 1 here, is going to equal 8. So that's what I've put here. And as was mentioned earlier, when you have imaginary solutions, there's always going to be a plus and minus. So now the first thing is to convert it back into its factored form. And we'll go to the whiteboard for a moment here and see if we can see it perhaps without all that clutter. So we'll take this. So this is going to be f of x. Now remember, this is like a y here, and that's going to equal 3 sets of factors, where x was the answer, and in this case, -3 would become a +3. This would become x equals, well, x plus, get my eraser going here, x equals a minus I, x equals a positive I. Okay. Now, these are conjugates. So we can multiply these conjugates together and get x squared minus I squared. But we said in an earlier lesson, I squared is a -1. So the opposite of a -1 makes this a +1. And I'll just change that right now. And then this is x plus 3. So we're now going to FOIL this, and we get x to the third, our first. Our outers is 1x. I'll put it there, because our inners are going to give us a positive 3x squared. and our last is a plus 3. And again, this is y. And again, this was 0. So if we worked backwards, found the zeros of this, which were a negative 3, plus or minus I, we would get this equation. But now what they want us to do is substitute this value here, where x is a 1 and y is an 8, and see if this is true. So we're going to put our value for y, which is over here, is 8. And then this is going to be 1 cubed plus 3 times 1 squared. We're getting our x value from here, plus 1 times 1 is 1, plus 3. So 1 cubed is 1. 1 squared is 1. This is 3. And then this is 4. So this adds up to 4 plus 4 is 8. And this adds up to 8. So we have done this successfully. And let's now take a look at the book as to what they're showing here and clear this up. And they got this far, which is what we did here. And then they're going to substitute the one for the x and the 8 for the y, and they show it here that it checks out, and our a sub n is equal to 1. Now for our last lesson, or last part of this, is Descartes' rule of signs. So if we have a series of terms in a equation that has powers, we want to see how many times there is a change of sign. And that will give us the number of positive real zeros if the same as the number of sign changes or less than the number of sign changes by a positive even integer. If the function has only one variation in sign, then it has exactly one positive real zero. Now, when I first read this, I found this somewhat a little confusing. So I'm going to call on another professor who does a really nice job. And up over here on the upper corner, I should have a circle with an I in it, which is the link to the whole video. But the part I'm interested in is the way he treats this Descartes' rule of signs. And before we do, let's go to the second part of this, where the number of negative real zeros, if our function is either the same as the number of sign changes, if we make the function negative, or part B, less than the number of sign changes by a positive even integer. Now, if the function, when we change it to its negative value, has only one variation in sign, then it has exactly one negative real zero. But if it has none, then it has 0. All right, now let's take a look at what the professor has about this. Okay, here we go.
In this video, we're going to focus on Descartes' rule of signs. And with his rule, we can get an idea of the zeros of a polynomial function. For example, how many positive zeros do we have, or negative zeros, or even imaginary solutions. So let's look at an example. Let's say that f of x is equal to x cubed minus 2x squared minus x plus 2. Now let's make a table. So we're going to have the positive
And
zeros.
I think this table is a very good idea.
Zeros, the negative real zeros, the imaginary zeros, and also the total. Now notice that we have a polynomial with a degree of 3. So the total number of zeros should be 3. Now, to determine the possible number of positive real zeros, look at the sign changes for f of x. So notice that it changed from positive to negative, so that's one change. And then from negative to negative, that's no change. And from negative to positive, that's another change. So there's two changes. Now, according to Descartes' rule of signs, the number of positive real zeros is either equal to the number of sign changes for f of x, or it could be less than a positive even integer. So one possible answer is 2 because we have 2 sign changes. Another possible answer is 0 because 2 minus 2 is 0 and 2 is a positive even integer. So the number of positive real zeros is either 2 or 0. So let me separate these two values. Now what about the possible number of negative real zeros? How can we find that? So first, we need to write the function for f of negative x. So it's going to be negative x to the third power minus 2 times negative x squared minus negative x plus 2. Negative x cubed is negative x cubed. And then negative x squared is positive x squared times negative 2, so that stays negative 2x squared. Negative times negative x is positive x. So let's count the number of sign changes. So this doesn't change, that's 0. Here we have one change, and this doesn't change. So the total is only one sign change. Now, the number of negative real zeros is going to equal the number of sign changes, or it can be less than a positive even integer. And if you only have one sign change, the only possible answer is 1. Because if you try to subtract 1 minus 2, negative 1 is not a real thing for counting something. So you can't have a negative number of positive or negative real zeros. So if you have a sign change, if you only have one sign change, then you only have one possible answer for that. So we have one sign change for f of negative x. So there has to be exactly one negative real zero. So now that we have the number of positive and negative real zeros, we can determine the number of imaginary real zeros. So these three columns have to add up to the total 3. 2 plus 1 is 3, so therefore there's 0 imaginary solutions. But for the second row, we need to have 2 imaginary solutions because 1 plus 2 adds up to 3. So those are the...
Okay, so you see the use of a chart was very good, and he went over the idea of sign changes, wrote it out very well. So I think the chart was helpful and his explanation. Let's go on to example 6 now, where we're using Descartes' rule of signs. And here is our expression, our function. So here to here, this was positive, this is negative, so there's one sign change. This is negative to positive. This is another sign change. This is positive to negative. This is another sign change. And this is negative to positive, which is another sign change. So how many? Well, we have 4. Well, we can then divide 4 by an even number 2 and get 2. And we can divide 2 by 2 and we get 0. So the number of positive real zeros for this function is either 4, 2, or 0. And that's what we would put in that chart. I like the way they illustrated that. Now, as that fella explained, to find the possible negative real zeros, we change our function to its negative value. And then in so doing, when we get through, we then look at and see how many sign changes there are. Well, there's none there, none there, none there, none there. So there are no variation in signs when we do the negative real zeros. So there are then no negative real roots for our function. Now again, the other video takes it to its conclusion, showing how you would then use some of the principles that we've been working with, the rational zero theorem, and then using the synthetic division to see which of our roots are possible. Okay, this was rather a long lesson, somewhat complicated, and we'll wind it up here.